Yeah, I'll email you the homework right after this. It is not as long as your last homework. And so, but before we get into the topic for today, we left off here, and as soon as you guys left, I was like, oh, okay. So we were talking about how there's no way I'm going to take a second derivative of this thing to find out which is a min and a max. But here's what I wanted to talk about this because this is actually really useful. So let's think about this first. We have 4 solutions, and that makes sense because our thing looked like this: am4 plus some other stuff plus stuff equals 0. And so since this is a 4th degree polynomial, we expect 4 roots. And so we got 4 roots out of that. Although we didn't explicitly calculate what the complex ones were, we can rule them out because I'm sure that m is not a complex number. So whatever, all right? So that leaves us with 2 options. Either m is b over a, or m is negative, because I pulled out the negative cube root of b over a. Now, b and a, they were both positive numbers. So which one of these must be the case? Let's look at m. What is m over here? It's the slope. And look at that line. Remember, it's like the first thing we said. It has to be negative because of the setup of the problem. And it was one of the first things I said when I first wrote it up. I said, note that it has to be negative. Not thinking that it was going to help me out at all. And if I had thought that it was going to help me out, I might have made that connection there at the end. But this is one of the things, like, I'm so in the habit of noticing things like that because here at the end you could use that. Right? You could say, well, wait a second. We know that the slope has to be negative, so it can't be this one. Because b and a are both positive numbers. We know it has to be a negative slope, and so there is your answer. Okay, that's all I wanted to say about that. So, today, you both did the extra credit problem.
Yeah, the cubic one.
Right, and so this was the extra credit problem. This is from homework 19. Homework 19, extra credit, said, find the cubic approximation. Find the cubic approximation of f of x equals e to the x at x0 equals 0. Now, yesterday, Noah, you said, because we were doing stuff, we had some function, I don't remember, let's just pretend it was e to the x. And you said, you know, the line does an okay job, but the parabola is going to do a better job. And you said, so is parabola the best? And I was like, I thought, should I do this now? But I wanted to wait, because I wanted you to see the extra credit problem. And hopefully that would open your mind. Be like, well, everything we've been saying thus far has been like, the line does okay for a certain, and I hope that you did graph all of these on Desmos.
Yes.
And you could see when you actually graph the line and the parabola, that the parabola does indeed hug the curve for a longer interval. Did you see that?
Yes.
Right?
Except for with the sine. There was no
Except for,
parabola.
well, there was no parabola with sine. It's interesting. Maybe we'll figure out why that's the case soon. So, but whenever you had a parabola and a line, and you graphed all 3 together, you saw that the parabola does a better job. Did you happen to graph the cubic one after doing the cubic one?
There wasn't. Oh wait, no.
I mean, you didn't. There wasn't a prompt to do it, but maybe you're curious. And I could tell you that that trend continues. So, for instance, so here we go. You have your function f of x is e to the x. And we want to know, we're trying to find the linear approximation at 0. And you do that and you find that it's a line. You find that the linear approximation is 1 plus x. Then you go through and you do some stuff and you find the cubic approximation.
It's like 1/6 x to the 3rd plus.
No. Oh, I'm sorry. The quadratic.
Oh,
sorry.
yeah.
And yes. you find that the quadratic is 1 plus x plus 1/2 x squared. And it does a better job. Like, the linear one works there and then immediately pops off, right? The cubic is closer to it for longer. I'm sorry, I keep saying that because I see the Q. The quadratic hugs it for longer. And then if you were to graph the cubic one, which we're going to like go through and derive this, but the cubic one, which I called C of x, it actually does it for it's a better approximation for an even longer time. Right? It does an even better job. And so for those people keeping track at home, they didn't do this problem. So I want to actually go through and do this, and this would be good for us to do this. So we have, again, it's the same idea. You have an f of x. You're given a function. And the idea is I want to approximate this function with a polynomial. And so we say, well, okay, in this case, it's a cubic approximation. And so a general cubic looks like this, ax cubed plus bx squared plus cx plus d, right? Yeah. And the idea is, if I want this thing to approximate this thing, then I want at x0 equals 0, then I want the derivative at 0 to be the same. So we say you take the derivative of this guy, which happens to just be e to the x, and we want it to be the same thing when I plug in a 0 as this. So you take the derivative and you get what?
3ax squared plus 2bx plus...
But now we can keep going because it's not a line and there's more that we could actually do. And you say, okay, well I also want the second derivatives to match up when I plug in a 0. So we take the next derivative, the second derivative, and we get what?
6ax plus 2b.
Right. 3 times 2, right? I haven't written it out like that. Now we take the next derivative, the third derivative, because we can. And we say, well now let's go ahead and make sure that the third derivative matches up. And what do we get? 6a
plus 2.
There you go.
We'll do 6a.
Plus
Wait,
2.
Yeah, no, sorry.
No, that's just a constant, right? Okay, cool. Okay, and so then you say, okay, well I went through, I got all my derivatives. Now I want them to equal. When I plug in a 0 here, I want it to be the same thing as when I plug in a 0 there. Cool thing about doing this is, and you know, I wouldn't, if it were at 1, I wouldn't have written ax cubed plus bx cubed. What would I have done if I were trying to do it at 1?
The x minus 1.
Yeah, exactly. I would try to cheat the system so that, as you saw, I think probably by like the third problem you did, you're like, oh, man, why do I have to do it both ways, right? One of these ways is super easy, unless it happens to be at x0 equals 0, in which case the two different methods are exactly the same. So anyway, if it were x0 equals 1, we would have just jumped to the chase and said, okay, x minus 1 cubed, x minus 1 squared, x minus 1 right there. That way, when we plug in a 1, everybody disappears except for that one guy, right? But in this case, it's just 0. So these guys go away, and we're left with d equals e to the 0. What's e to the 0? 1. So d equals 1. Okay, then we do the same thing here. We say, okay, I plug in a 0 here, and it has to be the same thing as when I plug in a 0 here. I plug in a 0 here, that goes away. Plug in a 0 here, that goes away, and I get that c equals e to the 0, so c equals what?
1.
1. I do the same thing here. I plug in a 0, and I plug in a 0. And I say it has to be the same thing as when I plug in a 0 here. And so I plug in a 0 there, that makes that guy go away because it's 0. Then I get what? 2b equals 1, which means that b equals 1/2. Now, okay, I plug in a 0 here, and so that means I got to put a 0 there. And I say that that has to be the same thing as when I plug in a 0 here, which doesn't do anything. So that means that e to the 0 equals 3 times 2 times a. So that a equals what?
1/6.
1/6, or 1 over 3 times 2. Yeah, that's the same thing. And so, okay, I get it. Now I could write a formula for that, and it's a, because we know that this thing, this c to the x, where is it? Is that purple? It looks purple. Cx is ax cubed plus bx squared plus cx plus d, and now I could actually just plug these values in. A is 1 over 3 times 2. X cubed plus b is just 1/2 x squared. C is just 1, so plus 1x. D is just 1, and I get a 1 right there. And we can see that for a longer, if you were to graph it, you could see that for a longer interval, it hugs this curve, e to the x, even better. Okay? So, in fact, I want to say it this way. The polynomial approximation, and this could be for any function now, like, because I hope that you see this, and I hope you believe what I'm about to say, that the polynomial approximation hugs the curve for a greater interval, the greater the degree of the polynomial. So when the polynomial is of first degree, right, 1 plus x, but when it's of 0th degree, it's just a straight line going right here, right? Because, believe it or not, we could have a polynomial that's just a constant, right? And I could just say, okay, well then the 0th degree would be just the polynomial 1, and that's just a constant 1. Increase the degree, it does a better job because it looks more like it. Increase the degree, now you have a quadratic, you have a parabola that hugs the curve for a longer place. You increase the degree to a cubic, and now the cubic hugs the curve for even longer. Do you believe that statement, that the higher the degree, the longer the better approximation it is for longer?
Yeah.
Okay? I hope I've convinced you of that. Now, it turns out we can prove it. Actually, we can't right now because we don't have the tools to prove it. And it was a judgment call whether I wanted to be able to do this without proof. And I think it's important to go ahead and get all of this stuff down right now. Later this year, we'll be able to prove that indeed it does. And there's a statement I'm going to say in a minute that will make this more formal, that we'll be able to prove later. But I want to go ahead and get this in your toolbox now because it's so important. So, okay. If we get a better approximation for a longer interval every time we increase the degree, why stop at a cubic?
No reason.
There's no reason to stop at a cubic. There's nothing special about a cubic. In fact, we could choose an arbitrary degree of polynomial. Let's let that degree be n. Let's just say n. And let's think about it, because now we're going to kind of set up the same thing we just did. We said we have an f of x, and we have some polynomial. We did that with a cubic, right? Where I wrote down ax cubed plus bx squared, blah, 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 blah. Now, you'll notice I wrote these this way, where I started from the lower degree and worked my way up, and then I messed things. I don't know why I messed it up there. But in general, since we were talking about an arbitrary degree, and you'll see in a second, like, we might want to write it the other way around. Here's why. So, okay, we have an f of x. In this case, it happens to be e to the x. And now, since x0 is at 0, I'm not going to worry about doing my ax minus 0 cubed. But if it were anywhere else, I absolutely would. Like, if it were at 1, I would be writing this out like this. And we'll do that in a minute when we go to do this in general. But right now, we have a specific example of e to the x. And now, instead of limiting myself to a cubic or a quadratic or a linear, I'm going to say, you know what? Let's just get an arbitrary polynomial. We're going to call it t. What degree? Well, It's arbitrary. Let's call it n. So I'm going to put a little subscript n right there so we know. And you've seen me do this before, right? Like I've said, like a polynomial of nth degree, and then I write stuff out like that, and I put a little n right there. It's pretty standard that you do that. When n is an arbitrary number, or whatever is an arbitrary number, you put a little subscript there. Whatever, who cares? Now, and well, so what? Do I want like A, B, C all the way down to n? Oh, no, that doesn't make sense. So what I'm going to do is I'm just going to choose that my coefficients, I'm going to call them A. Okay, and
and A plus.
and so what I also want to do is say there's like, it would be nice to say like this would be the third, so I'm going to call this coefficient A3. This is going to be A2. This coefficient will be A1. We'll call this one A0. That way that the coefficient matches up with the actual power. Okay. So working my way up from the bottom, a general polynomial of nth degree is going to be A0 plus A1x to the 1 plus A2x squared plus A3x to the third plus, oh man, I wish I had more room. I'm going to do it right here. Sorry, everybody. So f of x is equal to e to the x. And my t n of x is A0 x to the 0 plus A1 x to the 1 plus A2 x to the 2. Now, I mean, I could, if I wasn't going to do something with this, I'd probably chop it off there, put some dots, and then write my final one. But because of what we're going to do here in a minute, I want to have a bit more. And so, I'm going to go A3 x to the third, and did I want to, I did want to, did I want a to the fourth? Yeah, I did. And so I'm going to go A4 x to the fourth, and then all the way up to A n x to the n. So that's the polynomial approximation, the nth degree polynomial approximation of this function. And so, like I said, why stop at cubic? Let's just get this guy. Let's do it. So what do I need to do? Same thing I wanted to do. I would say, well, if I want this thing to approximate this thing really well, then at 0, I want all of the derivatives to be the same. So I need to, and what I want to do here is maybe I'll see a pattern. And this is what you're going to do for this. Is, well, actually, we're going to see a pattern. Okay, so here we go. So I'm going to say the derivative of this has to be the same as the derivative of this. And so I'm going to need to actually compute them. I'm going to take the derivative of this. It happens to be a really easy one to do. Now let's take the derivative, the first derivative of this guy. Now what do we get?
A1 n plus, I guess.
Yeah, this guy goes away, right? And now we have just A1 is left over.
Plus 2a2 times x.
2a2x plus 3a3x squared plus 4a4x to the third.
N x to the n minus 1.
Aha, right? This guy goes down by 1 degree. First derivative, and the derivative is of order 1, we have at n minus 1. Just thinking, I want to be able to spot patterns here. Now let's take the second derivative. E to the x is just e to the x. Now I take the second derivative, and what do I get?
That goes away.
Goes away. Now
2a2
2a2 plus
6.
How about 3 times 2?
No,
A3
x.
x
Plus
plus
3 4
4 times 3
a4
x to the x squared plus
N minus 1 times n
a to
times
the
a
n
n
to the x minus 2.
n minus 2. Oh, hey, look at that. When it's the second derivative, this last guy is n minus 2. Let's keep going. We take the third derivative of e to the x, and what do we get?
E to the x.
You sure about that?
Yes.
Okay. Now I take the third derivative of my polynomial approximation, and what happens to him?
It goes
What happens here?
just 3 times 2, 8,
3 plus
2 times 4 times
4
or
times
4
3
times
times
3
2.
times 2.
4 times 3 times 2, a4
x.
x plus, and then I would have done it with the fifth one. And I'm willing to bet that at this point the fifth one looked like 5 times 4 times 3
Yeah.
times a5.
Yeah.
Okay, patterns. This is really important that we're noticing patterns. Now I take the derivative of this, and what do I get?
N minus 2 times n minus
Or
How
n
about-
times
yeah,
n
there's
other way.
one.
How about that way? Yeah, patterns, patterns. X to the,
N minus 3.
oh, so when it's the third derivative, it's n minus 3.
Yes.
Cool. Okay, now, we're gonna do one more. So I take the fourth derivative of e, and I get,
E to the x.
Yeah.
it's still e to the x. Okay, so I take the fourth derivative of this guy, and what happens to him?
Gone.
Gone.
4 times 3 times 2.
4 times 3 times 2, a4, and then whatever the fifth one was, and then whatever the sixth one was, and now I got what?
N minus 1
minus 2
times
N
x.
minus 1, N minus 2,
Times 8,
N minus
x to
3,
the n minus 4.
N, x to the N minus, oh hey look at N minus 4 when the derivative is of order 4.
I think we have a pattern.
I think we have a pattern. I think we have a pattern. And so let's say that we continued this on and I took the nth derivative of e to the x, and what would I have gotten? It would have been e to the x. And so I continued this on and I took the nth derivative of this.
And all
Well,
those are
all of those would have been gone because the
Oh, yeah.
term before this would have been a n minus 1 x to the n minus 1, and by this point he would have been gone, right? The one before that he would have been left without one of these, and that now he would have been constant, and then we take the just in every case you had a constant, you take the derivative, disappears. So when the derivative is 2, a1 disappears. When the derivative is 3, a2 disappears. When the derivative is 4, a3 disappears. So when the derivative is n minus 1 must have disappeared. And what would I have been left with? Well, each time we took
n
another derivative.
factorial
Oh, yeah.
times a
Yeah.
n.
Yeah, and so look at that, right? Because it would have been n minus, so let's just imagine that n was 6. Well, it would have been a 6, then times a 5, then times a 4, then times a 3, then times a 2, right? And then we'd finally would have been back down here, and it would have been n minus 1, n minus 2, all the way down to, and let's think about it. When the derivative was 4, it ended up with x to the n minus 4. When the derivative is n, it would have been x to the n minus n.
Which is just 1.
Which is, what's n minus n?
0.
0. Oh, which is, you're saying the whole thing is just 1. I was like, it's not x to the 1. It's not, what, you're not paying attention. Yes, so this is 0. So this would have just been a 1. The thing before it would have come all the way down to 5 times 4 times 3 times 2. The a to the n would have been there. You take the derivative of it and it goes away.
So
And
it's
like-
just n factorial.
That's pretty cool. Now let's think about this. So we've done all the work. Now we've done the work. Now what we want to do is we want to plug in our zeros, right? Because we're doing it at 0. If it were plugging in a 1, we'd be plugging in a 1, but this would look different. We'd have an x minus 1, an x minus 1, an x minus 1. And so that, why would you do that in the first place? Well, so that your calculations get really easy with this step, right? I plug in the thing that's going to make almost everybody disappear.
There's no x's to plug it into anymore. It's just n factorial.
What now? Well, yeah, that's well, we're going to do this with everybody and watch what happens. Why? Because that's what we did last time, right? We found each one of these coefficients.
Yeah.
We're going to do the same thing, and we're going to arrive somewhere here in just a second. So let's do that now. Now we've done all the work just the same way we've done before. Now we're going to plug in the point I care about, which is 0. And when I do that over here, I'm not going to do this every time for this because that's just annoying. But when I plug in a 0, I get a 0, which is just a what?
1.
A 1, and I'm going to say that has to be the same thing as when I plug in a 0 over here. That makes all these guys go away. Okay? I do the same thing. I plug in a 0, I get a 1. It has to be the same thing as when I plug in a 0 here, which makes all of these guys go away. I plug in a 0 here, I get a 1. I say it has to be the same thing as when I plug in a 0 here. It makes all of these guys go away. I plug in a 0, I get a 1. I say that has to be the same thing as I get when I get right here. That makes all of these guys go away. I plug in a 0 over there, I get a 1. I say it has to be the same thing as when I plug in a 0 here. That makes all of these guys go away. And I keep doing that all the way down until I get to the nth derivative. I plug in a 0, I get out a 1, and I say that 1 has to be the same thing as when I plug in a 0 here. It's just a constant. There's nobody goes away. He's just right there. Now let's do the work. Now we have something interesting. And you'll notice here. Okay. So, remember what we were trying to do. We're trying to find the nth thing. We know that it goes a0 plus a1x plus a2x squared plus a3 and so on and so forth all the way up to anx to the n. And now we've just solved, we are able to solve for each one of these. So a0 is equal to 1. a1 is equal to 1. a2 is equal to what? 1 over 2. a3 is equal to what?
A2 is equal to 1.
Thank you. That's a that's nice, okay. And so, okay, A3 is equal to what?
1/6, or 1 over 3 times.
1 over 3 10. What's a cool way we could write that?
3 factorial.
Can we write 2 as 2 factorial?
Yeah.
Yes.
And 1 is 1.
Can we write 1 as 1 factorial?
Yes.
Can we write 1 as 0 factorial?
Yes.
You see a pattern?
Yes.
So what's A4?
1 over 4.
1 over 4 factorial. What's A5?
1 over 5.
1 over 5 factorial. What's AN?
1 over n factorial.
Holy moly. And so what we just got here.
N factorial over n factorial.
What?
Because an is 1 over n factorial, and then that's just n factorial times 1 over n.
Well, wait a second. Now we just need to replace these because remember what this is. A1x, A2x squared, A3x cubed, plus all the way up to here. Now we're just replacing these.
Yeah.
And so A1, and I'm going to, although this is good, I'm just going to write them as ones.
Yeah.
Okay? And so we get, this is just 1, plus 1 times x, plus 1 over 2x squared, plus 1 over 3x cubed, plus, and we could keep going, and it would be 1 over 4x to the 4th, all the way up to 1 over nx to the n. Is that cool or what?
So then we can, that equals e to the x.
Well, it's an approximation,
Well, yeah.
right? And so,
But
and
if you let n go, then
so check this out, okay? So this, like I said, right, we have, and I want to make sure this is how I want to do it. So I'm going to rewrite some of this stuff up here. In fact, I want to get rid of this. It's a pretty easy formula to remember, okay? And so what we have then is the nth, so for a given f of x, e to the x, we have that the nth degree Taylor polynomial, that's why it's a t actually, and I'll explain this in just a second, is this. Okay, now, if you were to graph this guy,
wonder what
to depending on n, if you let n get really big, what did I say? Right, it's always going to match up right here as by design.
Eventually it would have to go down, right? Because it's like,
Well, yeah, and that's the thing. Eventually, like if n is, say, 100, then he's going to go up like that. If n is 101, then he's going to go up here and down here. But the bigger n is, the greater the distance it's going to be before he branches off here. Right? And so, now here's the thing. I mean, he's never going to get bigger than that, actually. Now, so the dotted, of course, is the Taylor approximation. Okay, here's the thing. In fact, I want to do this in different colors. I'm sorry. Give me just a second. So this guy's dead on, and eventually he breaks away. It's dead on, eventually breaks away. Okay, so here's Tn of x. And here's f of x. The x0 that we used happened to be right here, x0. Now given any other x, let's say this x right there, and it could be really, 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 really big. It could be 700 billion, or it could be 2, whatever, right? When you plug that in, there's going to be some difference here. You plug that in here, and you get your f of x as an output. You plug in the x here, and you get a different value for your Tn of x. Then this distance right there is called the error. We talked about this last time. It turns out that this is your error right here, right? That's the distance from that point to that point. And whether or not one's above the other, that's why we use absolute value here. Okay? It turns out, we will be able to show this later on in class, it turns out that this value, for any f and any t, or well, for any f, you get your t in the same manner that we just did. It turns out that this is less than or equal to m times this distance, x minus x0, whatever that distance is. And you can see, it's as it gets bigger, this gets bigger, raised to the n plus 1 over n plus 1 factorial. And here's the thing, we will also prove this. Your book just hand waves it away, but we will prove, we will prove that you give me any value of m, and you give me any distance, no matter how large. It could be a billion, it could be a trillion, it could be the trillion raised to the trillionth power, I don't care. If you have that, and then you raise it like this, and you do this, it turns out that the limit as n goes to infinity of this is 0. The denominator, factorial, always wins out over raising to a power. It just does. So like, for instance, 2 raised to the n over n factorial. Eventually, n factorial gets way bigger. And you
wait,
can kind
so
of...
the bottom approaches 0 faster?
No. The bottom blows up faster than the top. And look, this is what I'm saying, right? So like when n is 1, you have 2 to the 1 over 1 factorial. When n is 2, you have 2 squared over 2 factorial. When you have to the third, you have 3 factorial. It's still 8 over 6. It's not quite there yet. But when it gets bigger, like you have 2 to the, let's say, 5th over 5 factorial. Now you're starting to see that the bottom's winning out. 2 to the 5th is what, 32? 5 factorial is 120. 2 to the 6th is like 64. And 6 factorial is like 720, I think? And so on and so forth. Eventually, the bottom blows up way faster than the top, no matter how big that is. And since that's the case, check this out. Here we go. Here we go. Are you ready for it? And this is like I said, doing this, like if we could have proved, well, we will be able to prove this later this year. But I want to go ahead and do this now because, well, I have my reasons. But I hesitate to do something without giving you a proof. But I think what I just did is so. But it should be suggestive that this, like I said, every time you take a bigger one of these, it works for longer. That's what this means right here.
So would that mean that if n is infinity, would it just be the same graph?
So let's take a look at this, right? Let's take the limit. If we take the limit, well, there's no. This is obviously anything is bigger than or equal to 0. Anything in absolute value, right? That's always bigger than or equal to 0. And so this must be true. The limit as n goes to infinity of this. In other words, you take your e to the x and you subtract off this, whatever that is, for any value of n. And you get that distance right there. Now we're gonna imagine that this guy is going on forever, is what we're doing right here. And since that's the case, and Victor, yes, you're what you just said is the case, right? That, well, this limit is 0. And so you have 0 is less than or equal to the limit as n goes to infinity of the difference so that distance must be what?
0, because of
The distance must be 0. And if that, and then that's true for any value of x that you could have possibly plugged in. And since that's the case, then those guys must be equal. And so, in other words, f of x is equal to the limit as n goes to infinity of this guy right there. In other words, if I do this dot go on forever, this is exactly the same thing as e to the x. This is what e to the x is. We could have started with this as the definition of e to the x. Although that would be hard to start with, right? Like, e to the x is this. This is polynomial that goes on forever. And what we have now, this is called the Taylor series of e to the x at x0 equals 0. Okay, here's the thing. Yes, I did want to skip that. Good, I'm glad I didn't get into that. Now, let's check it. Let's check it. This is really cool, right? Okay, we have e to the x. I claim that's equal to 1 plus x squared over 2 plus x cubed over 3 plus all the way up to x to the n. Oh, no, x to the n over n. And on and on and on forever. Let's take the derivative. Take the derivative of this side, and what do you get?
e to the x.
It's still e to the x. Now, take the derivative of this side. What happens to 1?
It's gone.
It's gone. Take the derivative of that. What do you get?
1. And then just 2.
2x to the 2 times 1.
And then there's
So just x. Okay, so now I take the derivative of this, and what do I get? 3x
X, just
squared
x squared.
over 3 times 2
no.
times 1
so x squared over 2.
plus x squared over, not just 2, 2!
Yeah.
Okay, now I take the derivative of x cubed. The 3 comes down, we get x squared, and that's over 3! And so let's see what happens. Oh wait, I just did that.
Wait.
That's what I just did.
The
Okay,
fourth.
and so yeah, let's do the fourth. We have this right there. We're gonna take the derivative of it.
Oh, so it's 4x to
The 4x to the
Third over 4 factorial.
over
So 4's go away, so
4
3
times
factorial.
3 times 2 times 1.
Oh,
So the
this is
4's go
okay.
away, and we're left with 3 factorial. So
the power
x
is
cubed
just-
over 3 factorial plus, and I go on and on and on. Now I take the derivative of this, the n comes down, I go n minus 1, we have n factorial.
So then n minus 1 factorial. And then
So then, yeah, the n cancels out and we get an n minus 1 factorial. And x to the n minus 1 over n minus 1 factorial. Imagine that there was the next one, x to the n plus 1 over n plus 1 factorial, and he kept going on forever. The n plus 1 comes down, so we have n plus 1 factorial is the same thing as this, times n minus 1 all the way down to 2 times 1. We had x to the n plus 1, the n plus 1 comes down, and we decrease that down to n.
So it's just x to the n over n.
So x to the n over n factorial. And on and on and on forever. Does that work or what?
Yeah.
Is that cool? Is that cool or what? So again, this is called a Taylor series. Oh, yeah, we're not going to go into that. I'm going to hold off. I'm going to hold off till Tuesday for that. That's going to be really cool. At least I think it's cool. But I teach math, so.
Could you do it with functions other than e to the x?
Oh yeah, and that's what we're about to do right now. So here we go. Here we go. So that one, by the way, that formula is too easy to remember. It will behoove you to remember that for the rest of your life. That e to the x is the Taylor series. 1 plus x squared over 2 plus x squared x cubed over 3, and so on. Now we could have evaluated it at a different point or whatever, but yes, now here we go. In general, you're given some function, f, whatever it happens to be. And what we could do is derive the nth degree Taylor polynomial for it. Now, we are going to consider what it's like if we did it this way, right? We're going to do it at some place. And we go all the way up to nth, and we go x minus x0. Why are we doing this? Well, to make calculations easy, right? And I mean, we could imagine that we just continue this on, so it's not the nth, it's the actual Taylor series. The difference between a polynomial and a series is that a series goes on forever. Polynomial does not. But whatever, however you want to think about this. So we just do the same thing. We take the derivative here, and we take the derivative here, and what do we get when we take the derivative?
A0 goes away.
It goes away, and then what do we have here?
Just a1.
Just a1, right? Because a1 times that is a1x minus a1 x0. This is just a constant, whatever it happens to be, and so when you take the derivative, it goes away, and all you're left with is just a1. Same thing here. Okay, so the 2 comes down. We get 2a2 and then x minus x0, then plus 3a3 x minus x0 squared, plus, and we kept going.
Then you have to. Oh wait. Do it again, right? Because of
The n minus 1.
n minus 1. Right? What were you saying, Noah?
Because of the chain rule, wouldn't you have to do it again?
Well, yeah, and we did. It just turned out that the derivative of x minus x0 is what?
Oh, it's just 1, yeah.
Yeah. And so that's a nice thing about this, right? So like you take the derivative of x minus, say, 5 raised to the 9th power. Well, the 9 comes down, you go x minus 5 raised to the 8 times the derivative of x minus 5. What's the derivative of x minus 5?
1. Yeah.
It's 1. Oh, nice. So that's what we're doing here.
Yeah.
That's what we're doing. Good catch, right? We want to make sure that we're good with that. So you take the second derivative. Now t2 and x equals, what happens here? What happens here? 2a2 plus
3 times
3 times 2 times a3 x minus x0 raised to the 1. I'm willing to bet that the next one would have been 4 times 3 times a4 x minus x0 now squared all the way up to
n minus 1 times n times a n times x minus x0.
n minus 2. There we go.
Yeah.
Okay, now let's take another derivative. So we take the next derivative. Third derivative. He goes away. What happens here?
3 times 2 a3.
And that's it. Okay, and now what do we have here?
4 times 3
4 times 3 times 2, a4. X minus x0. I'm willing to bet there was a 5 times 4 times 3. Okay. But anyway, and that goes on and on and on until we get to n. n minus 1.
Times
n minus 2.
a
A
to
to
the
n.
x minus x0 to the n minus 3.
And minus the same number as we're doing there, right? And so on and so on and so on until we get to the nth derivative. Now all of this hinges upon your function having all these derivatives at the point you care about. So like for instance, you couldn't do this.
Polynomial or something.
You couldn't do this with this guy at say 0.
Yeah.
You could do it at 1. You can do it at 4, that's fine, but at 0 you can't do it. All those derivatives have to exist.
You can't do it with a polynomial.
You can do it with a polynomial, it just turns out that forever and ever it's just 0.
Yeah.
And then you just get the polynomial.
And so the Taylor polynomial, the Taylor series is the same thing as the Taylor polynomial. And so, as you saw in one of your homeworks, right? Like, it turned out to be the same thing. When you did the quadratic approximation of the quadratic,
Oh, right.
you got the quadratic back.
Yeah.
Same kind of thing here, right? Okay, so, now let's do this. Tn, the nth derivative of the nth degree Taylor polynomial. He's gone, he's gone, he's gone, he's gone. The only guy that's left is this guy, n minus 1, n minus 2, and he would have gone all the way down to 4 times 3 times 2.
Times 1.
Yeah. And then that guy would have been gone because it would have been, well actually we could just say by the pattern, right? It is this right here. It's just that it was n minus 1, n minus 2, n minus 3 when it was 3. And so when you get all the way down to here, it would be n minus n, which is just 0, and so that's just a 1, so I'm not even going to bother to write it.
So it's n.
Now what's the next step? What did we do after we got all this information out?
We plugged it back.
We plugged, what did we plug in?
Zeros.
We plugged in a 0 only because x0 was equal to 0.
But now we plug in x.
Now we're just going to plug in an x0 because we're doing this in general. x0 could be 5, it could be 0, it could be 9, who cares? But when I plug it in, what happens to all these guys?
They're all.
That's so nice, right? And so let's just do that. I plug in, I'm not plugging in a 0, I'm plugging in my special x0. And when I do that, I plug in an x0. The x0s all kill each other. And we got that. I plug in an x0, whatever it happens to be. It could be 5, it could be pi, whatever. When I do that, that makes that guy go away. It makes that guy go away. It makes that guy go away. I plug in my x0, plug in an x0, that makes these guys go away. Plug in my x0, say that they must be equal, giving me these guys, blah, 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 all of them go away. I keep doing that until I get down to the nth one. And when I do that, there's no x to plug anything in for, and so that's what I get. Now let's see if we can figure out a pattern. Okay, so these guys are gone. It'll be easier to just not look at them. So I'm going to do that. I don't want to see them. Maybe I could rewrite all of these. So this is just, it'll look nicer if I write it like this. So we know that my A0 has to be that guy. My A1 has to be that guy. Now, this is the same thing as A2. So this says that the second derivative, when I evaluate it at x0, has to be the same thing as 2 times a2. This says that my third derivative at x0 has to be the same thing as 3 times 2 times a3. What do you think, oops, the fourth would
4
happen?
times 3.
4 times 3 times 2 times
A4.
a to the fourth. What do you think? I knew that this was that. Okay, what do you think that f to the 5th would have to be?
5 times 4 times 3 times 2 times
5 times 4 times 3 times 2 times
25.
a to the 5th, and so on, all the way down to, and we'd notice that this is the same thing as 0 factorial.
Yeah.
This is the same thing as 1 factorial. It's the same thing as 2 factorial. This is the same thing as 3 factorial. Same thing as 4 factorial. This is the same thing as 5 factorial. And so on until we get down to the nth derivative. When we plug in our x0, must be the same thing as n factorial a to the n. Now we have a formula. Because remember, at the very beginning, well, let's go ahead and get the formula. So, man, I wish I had a bigger board. So, we said that this was a0 plus a1x minus x0 plus a2x minus x0 squared all the way up to an x minus x0 to the nth. So all we need to do then is just find what these numbers are. Well, there's that number. It's the same thing as, and now if I just solve this, I'm going to come back now, give myself more room over here, and say, well, if that's true, then and I'm just going to write a0 equals f of x0. Here, a1 has to equal f prime at x0. Notice it's not a function. Once I plug in a number, I get an actual number.
Yeah.
Right? Same way we did with e. I plug in a 0, I get out a 1, and so I replace that with a 1. But now we don't have actual numbers and functions here. We just have a general function. And well, here we go. So a2 is equal to what?
F double prime of x0.
Second derivative evaluated at x. I plug that number in, I get out a number over what?
2 factorial.
Over 2 factorial. A3 is equal to what?
The third derivative of f times x0 over 3 factorial.
The third derivative, after I plug in that x0 over 3 factorial, and so on, all the way down to the nth, which is what?
Nth derivative of f. Oh wait. Yeah.
The nth derivative of f
Times x.
evaluated at x0. It's not just a function. I'm not plugging in a function here.
Yeah.
I divide it by what?
N factorial.
N factorial. And so now here you go. The nth degree Taylor polynomial is given by, of a function, is given by f evaluated there plus f first derivative evaluated there over 1, f the second derivative evaluated there over 2 factorial, all the way up to, you take the nth derivative, you plug in your special point, you divide by, and right there.
So
Now, okay, everybody got that? That's how we got this? This is now a formula you could use for the rest of your life. Please remember how we got it.
yeah.
Okay? And like, I mean, a lot of people, I swear, I've tutored so many people who like just, they've memorized this and they have no idea why. And then when it comes to like, well, think about how you got this. It might give you an idea of how you could solve this problem. Well, how did you get this? It's just a formula. Well, it's because you took derivatives and set them equal to each other. That's how you got these things. So, yeah. Okay, now, what do we say about limits and stuff? Well, if you keep going, if you don't stop there, then it is true that your function is equal to f at x0 plus f prime x0 over 1, x minus x0 plus f second derivative there 2 x minus x0 squared plus all the way up to the nth derivative at x0 over n factorial x minus x0 to the nth, and you keep going. This is important here. This means we are not stopping. We're going on forever and ever and ever. So if you go on forever and ever, then yes, it is equal for any value of x. It will work. Because like we said, you make it big enough, and it will go big enough. The error between your approximation and your actual function will get to 0. Or you can make it arbitrarily close to 0. And so if you go on forever, they're the same thing. You could also write this in nifty summation notation!
Yeah.
Now, check out what I did here. Instead of going up to n, what this means, if you have something, k goes from 0 up to n, and you take the limit as n goes to infinity, that is what we mean by writing that your index of summation goes up to infinity. That's what that means. And it means the same thing as this, just keep going. So when you see that, that means just keep going, and forever and ever. And when you do that, this is really nice because you take the kth derivative, and you're like, what's the 0th derivative? Well, you just didn't take the you just didn't take the derivative. And so that's how that matches up right there. At x0, you divide by k factorial, and you go x minus x0. So I'm really glad we did this last year. Because imagine having to learn this now, right? Like, wouldn't that be a pain? But you should be familiar with this, and you should know that that is that, right? Those are the same things,
Yeah.
right? Especially since we're going on forever, right? Now, if we did want to stop, I could just put an n right here. An n, that would be the same thing as that if we did stop. But we're taking the limit. We're going on forever, right? We're going to say this goes on forever. And when it does go on forever, then they are equal. This is called the Taylor series. This is a Taylor series.
Who is
And that, i.e. a series. A series is a polynomial that never stops.
No, who's Taylor?
I don't know, Joey Taylor, or maybe like Taylor Smith, I don't know. Some dude. I really don't know. I don't know. But they're named after that guy. So, okay. Okay, so this is a formula. Here's how you're going to use it. Okay, so commit this to memory. I think I've seen a tattoo of this before. Somebody tattooed. It was this right here. Somebody had this tattooed on them. It's cool. I mean, I'm a Mandelbrot set tattoo, right? And like, so I mean, I'm not hating on anybody here. It's not a dig. Okay, so okay, what we want to do is find, and in your homework, I'm just gonna say find the Taylor series for this at this place. What we want to do is find the Taylor series for f of x equals cosine x at, I'm not going to put it, I guess I'll do it right here, at x0 equals 0. That's going to make my life a little bit easier right there. Now what we could do, right, we could go through and actually write out my Tn and have a big long thing, and then each time take derivatives, right? I'm not going to require you to do that. I just want you to remember where all this stuff comes from, okay? But step one, if you want to, step one, we're going to need a bunch of derivatives, right? My goal is to rewrite this thing as this thing right here. And in your homework, I say write it in expanded form and in summation form, okay? So we're going to, and I suggest you do expanded form first. Yes, trust me on this. So watch. So now, okay, so in order to do either of these, we need a bunch of derivatives. So let's take a bunch of derivatives. And in general, what you do is you just keep taking derivatives until you notice a pattern. And then it's probably a good idea to keep taking derivatives even after you notice the pattern. Just get more than you think you need. So what's the derivative of cosine?
Negative sign.
Negative sign. What's the derivative of negative sign?
Negative cosine.
Negative cosine. Okay, what's the derivative of negative cosine?
Negative
Sine. No, just sine.
Positive sign.
And then it
What's
goes
the
back
derivative of sine?
to cosine. We had this on the
Cosine.
test.
Yeah, you did. And let's keep going, right? I mean, now we see, okay, there's a pattern. It'll be good to keep going with these, okay? So let's take a few more. What's the fifth derivative?
Negative sine.
Okay, and this gets a lot easier because you could just look above, right? Negative cosine. That's probably good, but we'll do one more since I have some room. Take the seventh derivative, and we get
Sine.
positive sign. There we go. Okay, now, okay, so that's step one. You take a bunch of derivatives. Now remember, it's not f of x that we're plugging in there, or f prime, or f the ith derivative. On your thing, I have some. I'm referring to something, and I have this. It's just saying any one of those that you're taking, any one of these. It's the ith one, right? It's like saying the nth one, right? It's that evaluated at x0. So let's evaluate them at x0. Okay, so x0 happens to be 0. How nice of me. So let's do it. What is f of 0?
1.
Okay, what's the first derivative?
0.
Okay, what's the second derivative?
Negative 1.
What's the third derivative?
0.
See a pattern? What's the fourth derivative?
1.
What's the fifth derivative?
0.
What's the sixth derivative?
Negative 8.
What's the seventh?
0.
Okay, see a pattern?
Yes.
1, 0, negative 1, 0. 1, 0, negative 1, 0. 1, 0, negative 1, 0. Okay, we got a pattern. Nice. Now, don't forget where this formula comes from. What you're doing here, right? And you don't need to do this part, but just don't forget what you're doing is you're setting these equal to each one of these that we have derived before, right? Once you plug in your 0, all that junk went away. And what we got was this stuff, right? Oops.
Yeah.
Right? So each one of these came from this,
Yeah.
right? And this is what we're doing. Don't forget this. This is important, right? But now, what we're doing now is we're getting each of those A's right there.
Solve.
In other words, and so in other words, we're plugging this in. And so to get the A's, we're just dividing by whatever this is. And yes, this is the same as 2 factorial. This is the same. Yes, that, blah, 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 blah. That's how it all fits in here, right? Okay, so, okay. Each one of those AK's is just the derivative divided by the factorial of whatever that was, right?
Yeah.
Right? Whenever the order of the derivative, you divide by that factorial, right? So in other words, what I'm saying is A0 is 1 over 0 factorial. A1 is your 0, who cares? A2 is your 1 over 2 factorial. Or you could also just say, well, we could just plug it into here, but don't forget where that comes from. Please. Please don't forget that this is where these coefficients came from. That coefficient right there came from, you took a derivative and blah, 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 and then you plugged in your x0 and all those guys that got left, and now you're setting those equal to each other so that your A2 happens to be the second derivative evaluated where it was divided by 2 factorial. That's what that is,
Yeah.
right? And we have now that f, the second derivative at 0, is equal to negative 1. So we're going to plug in a negative 1 like that. Okay? Okay, now let's write this guy out. So that's like, so we found all of these, right? Like really the only thing we needed to find was this, which is that. This, which is that. This, which is, oops, this, which is that. Yeah?
Yeah.
So and essentially I'm just plugging in these numbers right now. Okay? I'm going to do that. give myself some room. So I'm going to rewrite these right here, just so I don't mess this up. If I were doing this on a piece of paper, I would just do this in one place and then go down below it. Just to let you know, that's what I would do, okay? Okay, so now really we're just plugging and playing now. Like I'm saying, okay, I've evaluated all of those. Now I'm just going to take this information and basically plug it into this formula. And I'm going to say, okay then, cosine x, right, because we actually had an f, is equal to, okay, plug that in, 1, divide by 1, 0 factorial, it's just 1, so it's just 1. Plus, f prime evaluated at x0 was 0. So I'm not going to write that, okay? I'm just going to write a 0 for there, right? Because that's 0 over 1 factorial x minus 0 raised to the first power. That's still 0, right? So why bother? Okay, the next one, this f second derivative at x0 over 2 factorial x minus x0 is 0, so I'm not going to write it like that for this, right? But anyway, the 2 was a negative 1, right? So, I'm sorry, the second derivative evaluated there, this term right here is a negative 1, yeah? So when I plug it in, it should look like that, right? Yeah. So I can rewrite this, which I'm going to, like that, which I hope you do. If you ever have a Taylor series that you're evaluating at x0 is equal to 0, don't bother with the parentheses, right?
Yeah.
Okay. So negative 1 over 2 factorial x squared. Okay, so now for the third one, we get a 0. So how about plus 0? For the fourth one, we have plus 1 over what factorial?
4 factorial.
4 factorial times x minus 0, how about to the fourth? Yeah?
Yeah.
Plus, now I'm plugging things in, right? Now I'm on the fifth one, right? The fifth one says take the fifth derivative and plug in a 0. I took a fifth derivative, I plugged in a 0, and I got out a 0. Divide that by 5 factorial and then go x minus 0 raised to the 5th. It's still 0, so I'm just going to write 0. Okay. The next one says plug in, now we're at 6th. I took the 6th derivative and plugged in a 0. I got a negative 1. So that right there is a negative 1. So I put a negative 1 on top.
Over 6 factorial.
Over 6 factorial times x to the 6th. Can you see a pattern?
Yeah, it's just every other one 0 and then the others.
Okay, so, alright, so right now, and what I'm going to have you do in your homework is come up with this is your job, right? Find a formula for that guy. The nth term. It turns out that's going to be the same formula that you're going to use right here as well. And we'll get there in just a second. So, okay, this is where we need to get a little creative. We've done these before, actually, and this is why, again, imagine trying to digest all of this that I just told you to do. Take derivatives until you find a thing. Oh, and by the way, there's this thing called summation notation, and there's a thing called a series, and I'm glad we've done this before, right? Because the idea now is I want to be able to write this in this form. I want a formula for this, okay? Well, one thing I suggest you do, first off, let's get those zeros out of the way. And we're going to say, okay, that's 1 minus, and I'm just going to write this a little bit nicer like this, plus, just to kind of save myself some space. So there's that. Now what is it? Minus x to the 6th over 6 factorial. What's the next one? Plus or minus?
Oh, plus. Plus.
Plus what?
X to the 8th over 8 factorial.
What's the next one?
Minus x to the 10.
Over 10 factorial.
Ah. And so on and so forth, okay? So let's see if we can find a formula. Now, this is hard because there's two things going on. You have what I call a blinker, right? It goes positive, negative, positive, negative.
It was like right raised to the n minus
Yeah,
1.
what was that?
Yeah, and so that's what we're going to figure out. So right now I'm trying to get this into this form. My index is going to be k. Okay, so I'm going to go ahead and write. I know that now. Ooh, and here's one of the things. K may not start at 0. It might be the case that you're like, especially if the value of your function there is 0, then you might not want to start k at 0. Or you could get creative and start it at 0. That's cool too. But you don't necessarily need to start it at 0. In this case, I do, because for my formula to work, like, I'm going to need a 0 term right here, because there's a constant.
Yeah.
So I'm going to go, this is what I'm going to do. Under here, I'm going to write k equals 0, k equals 1, k equals 2, k equals 3, k equals 4, k equals 5. And this should help me. Now, I know I need a blinker, so every time k changes, the sign's going to change, right? And so, and I've already given away, I know that I want it to be -1 raised to something.
Yeah.
To the
So, is k going to work? When k is 0,
well,
that's
a 1. Yeah.
a 1. When k is 1, that's a
Negative 1.
-1. Is that what we want?
Yeah.
When k is 2, that's -1 squared is...
1. Yeah.
So that is what we want. Now, if you had done this and said, yeah, and then you go to check it, and you go, oh wait, oh no, it's wrong, it's opposite, just subtract 1 off, right? that's how you do that, okay? Now here's the hard part. So this is something that you've seen this before. Here's the hard part. We're trying to get this like that. And that actually takes care of that, because every time it was either plus or minus 1, right? Yeah. Or a 0, I'm sorry. A plus 1, minus 1, or a 0. So that takes care of that. But now, when k is 1, it's a 2. When k is 2, it's a 4. When k is 3, it's a 6.
so it's just times 2.
So we have,
Okay.
so let's think about this. It's x raised to what power?
2k.
2k, there you go. Over,
2k factorial.
yes, good, 2k, and
Yeah.
write it like this, factorial.
Yeah.
Okay? That's it, there's your formula. That is it. Now, check it, right? We're gonna say, okay, I think I got it. It should be as k goes from 0 up to infinity. And now let's just check it, right? Plug in a 0. Plug in a 0, I get a positive 1x to the 0 is 1. Over here we get a 0, so that's 0 factorial. Is that 1?
Yes.
That is what we want, okay? Now when I plug in a 1, I should get this. Let's see what happens. Plug in a 1, I get a -1.
Times.
Plug in a 1, I get a x squared. Plug in a 1, I get a 2 factorial. Is that the term that I want?
Yes.
Okay, let's do one more. When k equals 2, we get -1 squared. X to the 2 times 2 is 4. Over 2 times 2 is 4 factorial. Is that what I want?
Yes.
Okay, so we're good. All right. And so what I want on your homework then is this, right? So you go cosine of x is equal to this. Oh, and by the way, that's what cosine is. We could have started with cosine as the definition of this guy. Like we could have, like last year, I could have
There's a lot
said
of definitions.
cosine is defined like this.
There's a lot
And
of definitions of
everything we
cosine.
do, well, I know, right? This is a perfectly valid one. We could have started here. Said cosine is this, sine is, you'll find out in your homework. And oh, and by the way, what would you do if the power was odd? 2k wouldn't work. What would you want to do?
2k plus 1.
2k plus 1 would work if something's odd. Or then if you're trying to make that work, -1 might also work, but it might not. Be careful. So 2 plus or minus 1, you have to figure that out.
Yeah.
-1 is usually what you do. Okay? And so we could have started like that. So one more thing though, I'm also going to have you do it. So I want it done in summation notation. I also want it done in expanded form.
Yeah.
Now you could just go ahead and do this. Do the first few terms. You could do as many, or I mean, don't just do one of them. Like do some so you can kind of see a pattern,
Yeah.
and then do something like this, and then it's the same thing. It's just we usually use in instead, and so I'm going to say to n over 2n factorial right there. Okay? And so that's what your expanded form is. If you choose to do it with k, that's fine. If you choose to call this n, that's fine too. It means the same thing, right? Just make sure that you don't have any k's floating around there. It means the exact same thing. I don't care if you match them up. I don't care if you have n for one and k for another. Whatever, doesn't matter. But this is the expanded form that I'm looking for, and this part is super important, that you have plus forever, right? Meaning keep going, don't ever stop, and then you will get that this is exactly equal to cosine x. We're graphing e to the x right now, and what I was saying in class is that we have the linear approximation of e to the x works like that, and what you should have seen in your homework is that the higher the order, or the higher the degree of the polynomial you use to approximate this, the longer it actually hugs the curve here. So, as you can see, if I zoom in, right, when you're really, really, really close, when you've zoomed way in, then the linear and the actual function itself are virtually exactly the same, and so it works. But as we zoom out, right, we could see that the line pulls away from the curve. But when the line's pulling away from the curve, then the quadratic approximation is actually still doing a pretty good job. And you can see that here I'm turning it on and off. And you can see that when we're zoomed in this far, there's no difference between the curve, which we're showing in red, the e to the x, and the quadratic approximation. But then as we zoom out, we see, okay, it finally starts to pull away. But it's working, it's doing a better job approximating for a bigger interval, right, for a larger domain, until finally it pulls away. Now, I was also saying if we check out the 1 plus x, if we check out the quadratic approximation of this guy, which would then be 1/6 x cubed, again, it does an even better job than the parabola did, right? And here, well, now everybody looks kind of the same here. Let's get rid of the line. Everybody looks about the same, right? But then eventually, when we're out here, we could see that the quadratic has pulled away from the true, here we go. The red is actual e to the x. The quadratic pulls away from it, but the cubic is still doing its job just fine. It's not until we get further out that he finally pulls away and we get different values. Okay? So now what I was saying there at the end, what I suggest you do after you have your once you've figured out the Taylor series for this guy, is that you just sit here and start putting in terms, right? 1 plus x. Okay, and this is going to be in black. I want to do something different than black. Let's see what other colors we have. How about orange? Okay, which obviously is the same thing as this. Now, I'm going to start writing it the way that I would have done it. So over 2 factorial. And we can see that's exactly the same as the green. That's why it's over the green. Now we're going to go x cubed over 3 factorial. And that's exactly the same as the purple. Now let's see what happens when I add x to the 4th over 4 factorial. It's hugging that curve better, right? The orange. Now it's starting to get a little busy. Let's get rid of the linear and the quadratic approximations. Now again, we could go and zoom in and see this, but you kind of see right here that the orange is hugging the red much closer than the purple is. And that's going to continue to happen. And it's kind of interesting to watch as we start adding more terms here over 5 factorial. It's hugging that curve better. And so on and so forth. This would be the last one I do for this. Okay, so yeah, look at that. Okay, so now if you really want to, this is going to be cool. What you could do is just go ahead and put in the Taylor series as in summation notation. So what you do to get summation notation, you go sum, S-U-M, and it knows what to do. Now notice that the index is in N. N is the index of summation. I used K on the board. Again, it doesn't matter. Use whatever you want. But I'm going to, n goes from 0 up to what? Well, that's what needs to be variable, because we can't just put infinity in here. It's not going to work too well. So what I'm going to do is just call it capital N, and then it'll ask me if I want a slider for that, which yes, I do. So now I'm just going to put in the formula. Formula for this guy is really easy. It's just x to the n divide by n factorial. And yes, I want to add a slider for n, so I'm just going to hit return. It's going to give me that. Right now, it's computing, it's saying n is 1, so it's doing both the 0. When you plug in a 0 for little n, you're going to get x to the 0 over 0 factorial plus x to the 1 over 1 factorial. So really, that should be the same as the blue one here. So there's the red, yeah. See, this is the Taylor series, and the blue line is that. So that's the same thing. And what I'm going to do, I'm going to go in here and change these limits. I'm going to go from 0 to, let's say, 100. Okay, now as I bring this guy up, there we go, there's 2. And so right now, this, the red approximation, should be the same thing as this, the green. Yep, it is. That's the quadratic right there. Okay. If I bring it up to 3, now that should be the same as this one. Oops. Or is, oh, I'm not graphing it, sorry. So that should be the same as this guy right here, which, yeah, you can't see it. There we go. There's the purple, right? So now let's just go for broke. Let's just drag this and watch what happens. I'm going to pull this back a little bit so you can see. I also want to get rid of all of this right here. And maybe I'll change the color to make it look different here. So let's do our series, our Taylor series here in green. And the function that we want to approach is in red there. So now let's just drag it up and see what happens. As I drag it, right, we're going through higher and higher orders, and it's getting closer and closer. You cannot see what's happening out here on the right-hand side, but you could see what's happening here on the left. As we get bigger and bigger, it's just getting better and better. Okay, now if I were to mess with the scale up here a little bit, like if I went in and said, okay, make this wider in the x direction, then you'd be able to see that it's doing the same thing over on the right. It's just that it shoots up so fast that you can't tell. But what we can do, so let's do the one that we just did in class, cosine. So I'm going to get rid of this, get rid of these, and now let's do cosine x. No, what a pain. Okay, cosine x. There we go. All right, so there's cosine x. Let's see a few of them. Now, yeah, there's that guy right there. We're going to bring him down to 1. Okay. Okay, so our first, well, I guess the first is just 1, and I guess I got to put y equals 1, right? Okay, and yes, it works there at 0. So that would be the Taylor polynomial of degree 0, and it does a great job approximating cosine here at 0, but it does a really bad job everywhere else. Actually, it also works over here at 2 pi, but it's right. That's kind of an accident, right? Okay, so let's get rid of that and actually do 1 minus x squared. over 2 factorial. So this is kind of what I was saying to do there at the end. You just start adding terms and see what happens, right? So in the the terms of the Taylor series, just start graphing them. And you could see, oh, it does a really good job there. Now, you should have seen this in your homework. I think cosine, you had to find the quadratic approximation, and you should see, like, yep, that works really well there. Okay, the linear would just be the one that we just did, just y equals 1. Okay, now let's see if we remember this formula. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Oh, interesting. And you can see, again, right, the 4th degree polynomial does a better job, right? It hugs the green curve, the cosine curve, for a longer interval, right? The quadratic in black is already pulling away, right? It's pulling away from cosine, but the red curve, the 4th degree polynomial, is still holding on tight, right? And it's not until we get over to here, it's not until we get over to here that he actually starts to pull away, and so on and so forth. Right, now let's see what's going on. Let's pull out a little bit and see. Okay, so that's what's happening there. Now I want to do the same thing here, only I want to change this formula and just put in the formula that we found for cosine, right? 1 second, what was this color? Was that color green? Yeah, we'll do it in green too, that's fine. Okay, so the formula we found was, we started by writing it with -1 raised to the, it's the index, we did it in class as k, but n is just fine. So a little n, x raised to the, it was 2n. Now divide that by 2n factorial. Okay, now when n equals 1, it should just give me the straight line, the straight horizontal line. Let's see what it does. No. When n is 1, then it would be x to the 2 times 1, so it would be x squared. So that does give me the same that we got down here in black. You can see I'm turning that on and off. There's the black, there's the 1 minus x squared over 2 factorial. It's the same thing as when our index runs from 0 up to 1. It gives you those first two right there. So now let's just see what happens as we drag this guy and get bigger and bigger. And he's holding on for longer, and he's holding on for longer until we just keep going. And now there's no difference, is there? No difference at all. And so we zoom out and we see, yep, it's way out there that he's working, but he's still working. And so if we just keep going, it'll just keep doing a better job. Oh, now that's interesting. I could tell you what that's about, but we're not ready for that yet. Now, to be clear, that's not real. That's an artifact of graphing that basically the computer is just having a hiccup there. In the real world, that doesn't happen. It's that by the time you're getting out to here, you're computing, and you see it's having a real hard time with that. By the time you get out to, say, 57, you have something divided by 2 times 57. I don't want to have to do that. I'm going to embarrass myself. 114. 114 factorial. Let's pull up some Wolfram Alpha and see what that is. 114 factorial. Okay, a ridiculously big number, right? So that's 10, something on the order of 10 to the power of 186. That's ridiculous, right? So 1 over that value, 1 over that is a very, 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 very tiny number. And Desmos does not know what to do with that number. And so it's having some really hard times out there. But if we keep it down to a reasonable amount, even there, right, 41, I'm impressed, actually. Desmos is dealing with that very well. But the point here, right, is I hope that this convinces you. Because in lieu of a proof, I know we didn't prove that the bigger n gets, the closer and closer the Taylor gets to the Taylor series. Okay. Given a nth degree Taylor polynomial and of some function at some point, as n increases, right, the Taylor polynomial works on a larger and larger interval here. And you can see that's what we're doing. He's starting to, when it's small, yeah, okay, that's great. But the bigger it gets, the further out it goes, right? And I hope you believe that if you let that number go to infinity, then there is no difference between the Taylor series and the function itself.